Welcome to Unbounded Realm. My name is Geng. I work in Institute of Physics, Chinese Academy of Sciences. I'm interested in exploring the novel topological matter of states in solid-state physics. To answer this question, first we have to know what quantum computation is. So the quantum computing is a technology that uses the principles of quantum mechanics, such as the entanglement and the superposition of states, to process, store, and manipulate the data and perform very complicated computational tasks that the traditional computers cannot accomplish. In traditional computers, we use the bits to store information. So these bits can take either 0 or 1 in their value, where the 0 represents the off state and the 1 represents the on state, so the off state and on state. And when we have many of these qubits, we can have the 0 and 1 sequence, which is basically the foundation of most of our modern technology. And in quantum computers, on the other hand, we use the quantum version of bits, or we call them the qubits, to do the computation. So the qubits are very different from the traditional bits. For example, we can still use the two states, the 0 and 1 state, to represent the eigenstate of this quantum system. And this quantum system can stay on either the 0 state or the 1 state. And more than that, the system can stay on an arbitrary superposition of these two states, which provides almost infinite possibilities of the state of this system. Also, in the quantum mechanics, these states can entangle with each other, meaning that the manipulating of the state of one of the qubits will change the other. So in that case, we can manipulate many of these qubits simultaneously. This makes the process much faster. And on these spatial platforms, people can design very smart algorithms, or we call them the quantum algorithms, to solve very complex problems in much more efficient way. I believe many of us have heard the news that a quantum computer solved a problem in several minutes that a classical computer needs tens of thousands of years to compute. So that's where the supremacy is, and it is a real thing on this problem. And regarding the future, I would say personally I'm optimistic about it. And right now the quantum computation is still in its infancy and is far away from our expectations. I believe eventually we would overcome all the obstacles and get there. The major issue right now is that the current quantum computers are mainly designed to solve specific problems. However, the public's expectation is that their quantum computer can solve any problem instead of a specific problem and replace their classical computers. That's where the gap is, and that's what needs to be solved before you have a quantum computer at home. Yes, if one could really solve the problems we have just mentioned, then the quantum computers will definitely change our lives in all respects. For example, you will have much more powerful computers. You will have smarter cell phones. You can gather information in a much more efficient way, and you can know the answer of the problem you would never solve. So you would have a much more cooler lives. As we have just talked about, the major challenge or the final goal is to make the quantum computation universal. And to get there, we have to overcome many issues. For example, one of the limiting factors is the number of qubits. It is not that simple to integrate many qubits on a single chip and allow them to entangle with each other. And also, the quantum systems are always connected to the other systems, which are usually described as environment. The environment produces lots of noise, which leads to the decoherence of the quantum system. And in that case, the quantum systems lose their information and produce errors in the calculation results. So we need more qubits and we need better qubits. There are still many other issues, such as the necessity of using ultra-low temperature in many quantum systems, and we have the difficulty in controlling each of the qubit. There are actually different routes to realize quantum computation, and the topological quantum computation is just one of them. Right now, the most widely known route is probably the quantum computation based on superconducting chips. This is also the type of quantum computers that Google and IBM are developing. In China, we also have many teams, for example, in USTC and IOP, working on this type of quantum computing. And there are also other routes, for example, the quantum computation based on photons or based on color centers, and so on. And topological quantum computation is based on a specific type of topological states. These states is very special in that they have the advantage of being robust against the environmental noise. We have just mentioned that the environmental noise creates errors in the calculation result. And one way to solve this problem is to do the error correction. The idea is to use many, let's say tens of thousands of qubits to protect a single qubit. And the former ones are called the physical qubits, and the latter one is called the logical qubit. We sacrifice all those physical qubits to get an accurate answer from the logical qubit. However, this route is not very practical at the present stage. Other method to solve the problem is to perform the so-called topological quantum computation. So these topological states are naturally robust against the environmental noise. So the environment will not cause the decoherence in these states. So if we could make this kind of topological qubits, then we don't have to sacrifice any physical qubits, and each of the topological qubit is actually a logical qubit.